Now we can get into material that I know you've all been waiting for, the discussions about life beyond this planet Earth. Are we the only species, the only intelligent organism in this entire universe? Or is the universe flooded with these things? Honestly, we just don't know. Personal opinion, I think there are other intelligent civilizations out there, but we just haven't found them yet. So with that, let's start to summarize where we think life is. Some of this material, if you follow through these lecture series, you'll have seen some of these planets before, but let's go through this. In terms of starting off with our solar system. You may recall at the beginning of this video, we talked about that meteorite that we know to be a Martian chunk that's thrown out of the cosmos. And that may have microbial fossilized organisms. But there are other reasons to think that there could be life, at least previously on Mars, if not currently. One of those would be ice caps. We found frozen ice sources of water on the surface of Mars. Another one that's led to a wonderful speculation of information is methane that we keep finding in the atmosphere. We keep looking at these, what's happening is that UV rays are coming in, breaking apart methane, and leaving us with this photochemistry, producing formaldehydes, methanol, carbon dioxide mixed with it. And so the question is, well, what's the source of the methane? And some possibilities are microbial life underneath the surface where there is potentially water mixing around with rock. So the water mixed with the rock interacts with microbes. That might be a source of methane that's getting eked out onto the surface of Mars and then being photodisassociated and breaking down on the surface. So on Mars, we're finding indications of higher levels of complex chemistry. And higher levels of complex chemistry is an indicator of life out there. Another candidate in our solar system is one of the moons of Jupiter, Europa. So here's a picture of the moon superimposed onto a different satellite's images of it. And you'll notice there's this clear plume of material coming out of the surface of Europa. Well, one possibility is that we think that underneath the crusty surface of Europa is a literal ocean powered by tidal forces. And that ocean could be jettisoning molecules up into space, and some of those are landing back down onto the surface. And just like on Mars, photons are coming in, photodissociating these complex molecules and breaking them down to simpler, lighter ones. So we're seeing traces that indicate that there may be a bigger soup of complex chemistry on Europa, just underneath the surface. You may remember discussions about the Enceladus moon of Saturn. And Enceladus helped fuels one of the diffuse G rings around Saturn. And so you see these literal streams of water being jettisoned out of the moon's surface. Well, some things to discuss. Talking about the possibility of life there is, one, is there water? Some may call this bias, but we know for a fact that water facilitates chemical reactions. And anything that facilitates chemical reactions increases the probability of living organisms being there. And that's why there's always this search for water. Water helps chemical reactions happen. But having water isn't sufficient for life to be there. There also has to be enough energy going around. If there's not enough energy floating around there, then you can never build up the complex molecules. And so the moon, like Enceladus, one of the issues is it too darn cold? What are its sources of energy? The tidal forces from Saturn? Enceladus is pretty far out there. So it's this tough proposition. Yes, we know there is water there. We see it being jettisoned out of its surface. But is there also enough energy present to sustain life forms? We just don't know yet. One more potential candidate in just our solar system is Titan, which is another moon of Saturn. But Titan literally has its own atmosphere. It's slightly larger than the planet Mercury. And we actually have seen potential lakes of hydrocarbons. So if there is life there, it will be drastically different from the life we find here on Earth. But it does have the necessary materials, some kind of fluid to facilitate chemical reactions happening, and enough energy present to continue that chemical evolutionary processes to build the complexity out there. So obviously we're going to do our best to send probes, send satellites, and maybe someday people to all these different objects inside our solar system in our hunt for extraterrestrial life. But what about outside the solar system? What can we say about life outside of the material that we can reach? Because I will say absolutely definitely, if we can never send a probe, how can we tell if life is out there? And I'm adamant here. I'm going to stand my ground and say, absolutely yes, we can never send a probe to those stars. Let's do just a simple assessment, calculation here. Let's say we got into our Starship Enterprise and we wanted to fly to Proxima Centauri, the nearest stellar neighbor, only 4.2 light years away. So it's simple, all right? You get a ship that can go the speed of light and only take you 4 years to get there. Right. Obviously, we can't travel at that speed of light, but how about we calculate how much energy would be necessary for a round trip, take a ship, fly to that star, and come back. And let's do what we're going to call some reasonable estimates. You can't move at the speed of light, but let's say we're going 70% the speed of light. So if Alpha Centauri is 4.2 light years away, then moving at 70% the speed of light, our round trip to go to the star and back will be about 12 years long. Now, in this calculation, how much energy does it take? We're going to assume a very idealistic sample. We're going to say that our engine runs 100% efficiently. Every last ounce of whatever our fuel is consumed, and all of that goes to maintaining our energy to get there and back. How long will this take? 12 years. How much energy? The amount of energy to get a ship moving that fast and traveling back, that amount is equal to about the same amount of energy that the US could consume in several 100,000 years. We would have to divert every single energy consumption that we have. No cell phones, no radio, no television, no photography, nothing. We'd have to divert every single one of those energy sources to fueling our spaceship to make its 12-year journey to Alpha Centauri and back. So yes, I am very adamant in claiming that we will never go to those stars. Outside of some new technological advancements where we can somehow violate the speed of lights, which I do not see happening anytime in the near future. Call me back when it does happen, or dance upon my grave. I might be dead long before or that comes about. But I will stake my ground here. We're never seeing these stars. We're never going to send material out there. Obviously, we're going to try, but in our lifetimes, we won't see the benefits there. So with all of that, how do we detect life outside of the solar system? Well, we have a couple of tricks. Our first method is to find planets in the habitable zone around a star. All right? What do we mean by habitable zone? Is that the star is releasing its solar energy, radiating things, and depending on the distance away, the intensity of light is going to diminish. The ratio of energy per unit area goes down with distance. And so if you're too close to the star, if you're too close to the star, any water there is going to vaporize, turn to a gas, and float away. If you're in the habitable zone, well, then you get liquids. And liquids are very useful for chemistry. So this is what we mean by find the habitable zone. Find planets that live in the habitable zone of their stars so they potentially have liquid seas or oceans on them. Go too far away, things are going to chill off, and that liquid sources will turn into ices, and the ices can't facilitate chemical reactions. So our first trick in trying to find life outside the solar system is any stars in these habitable zones. Now remember, depending on how big or small this star is, the distance to the habitable zone will be different. And that's just dependent on the star we're discussing. We've actually had a lot of successes finding planets in the habitable zone. Here is Kepler 452b. This is a planet that is only 1.6 times larger than the Earth, and it's orbiting its star in the habitable zone. So, we are already having success finding planets out there that potentially are inside that regions of water on that surfaces. But there are other tools here. Finding stars or planets in the habitable zone isn't our only way to tell if there's potentially life out there, because there's a huge difference between potential life and absolutely knowing for certain that there is life there. And that's what we want to find. You want to know a great way to tell if there's life on a planet? See if there's fire burning on the surfaces. Think about this. What is a fire? Fire is a rapid acquisition of oxygen. Oxygen's being consumed, fueling this chemical reaction. Right? Well, living organisms, put that oxygen there in the atmosphere. Let's look at Earth's history. Here we're looking at Earth and billions of years ago versus the amount of O2 present in the atmosphere. And starting around 3.2 billion years ago, there was this photosynthesis of oxygenic material. So the first cyanobacteria are consuming and wasting oxygen. Oxygen is their waste product. They're spitting in the atmosphere. They're literally dumping O2 into the atmosphere. And as they started to reproduce and multiply and become more and more prevalent, the amount of oxygen in our atmosphere kept going up, kept increasing. And this continued on in this trend until relatively recently, where it finally just stabilized, where you have things like the algae that have taken over some of that photosynthesis. So let's look at what we call biomarkers in the atmosphere. Scan of the planet, and you see the amount of chlorophyll concentration. Right? Earth has what we call a photosynthetic biosphere. The material in our atmosphere, the material in our oceans are constantly trying to photosynthesize. And these are more signs of living organisms. How much oxygen's there, what kind of reactions are seen. Recall, if we're ever fortunate to see a planet on fire, we're almost absolutely certain that there's going to be life present there. So a biosphere is a combination of the atmosphere, surface features, oceans, everything culminating into this biomarkers of the planet. Right? So organisms, life, has a huge impact on a planet's biosphere. We can see detections of the changes of oxygen present in the atmosphere. See big fires, see chlorophyll filling out photosynthetic regions across the surface of the planet. So to put this in perspective, famous image here, the pale blue dot right there. There's an image taken by one of the Voyager spacecrafts. Turn around, get one last glimpse of image of Earth. Alien species, when they're scanning the cosmos, they're going to detect the biomarkers of Earth. And those biomarkers are going to be the indications that there's life present on this planet. So here, this is a personal prediction by your instructor. I think that the first evidence of extraterrestrial life will be found by studying the atmospheres of an exoplanet. The first pictures of alien life will not be some microbial bug floating around on a rover. It won't be some picture of people hanging out with ET. It's literally going to be a picture looking at the atmosphere of an exoplanet, and from just a statistical analysis saying it is improbable to impossible for that planet to have that kind of biosphere without life sustaining it. And so I predict I wager it'll be about 50 years from now. We'll get confirmation of the first alien life out there in the cosmos by finding that planet's atmosphere.